Hey guys, I'm very, very sorry about that. Good to see you all, and I'm amazed that there are still people here. I am somewhat late for class today, but I was getting a vaccine, in case some of you know. The solution is to not do delivery. Yes. Okay. So in any case, just letting you know what happened. I was getting a vaccine because somehow we're able to get vaccinated now, and then when I was getting the vaccine, it said you can make an appointment for a particular time, and it'll take 10 minutes. And I was like, I can do that. And then it turns out that it's more than 10 minutes because there's like a huge number of people out there. And of course, the biggest mistake is like, whenever you go and do something, you'll probably notice that whenever you're in a line, it seems like there's tons of people in the line. And that's because there's a correlation between times that are convenient to you and convenient to other people. And so I made the mistake of being like, yeah, sure, lunchtime works for me. Oops, everyone on their lunch break was at the place. Anyway, so I'm here. Let's go and talk about graph theory. Here we go. Back to what we were doing last time. Well, a new thing now. So we're moving to a new topic now. So last time we talked about this Hamiltonian cycle thing, and we found out that there are ways to know that a Hamiltonian cycle exists. Well, now this time, I'm going to talk about something that seems different, and it is different, but at some point, like later on, maybe next week, the whole things will connect together in an unexpected way. But today, I want to talk a little bit about a notion of, we talked about connected graphs, right? And we were like, connected graphs, if they have no cycles, they're trees, right? And so I'm just going to remind some things that we had here. Remember that if you had a connected acyclic graphs, that's the definition of a tree. Okay. Now, we also had all this interesting stuff where we were like, oh, by the way, the number of edges is the number of vertices minus 1. So like we knew that. We knew that somehow the number of edges was equal to number of vertices and then minus 1. We also found somehow they're like minimal in some sense. It's actually, we also found out that if you have a connected graph and it's like minimally connected. So if you have connected graph such that deleting any edge disconnects it, well, that actually tells you that you have a tree also. We kind of talked about some things around this. If you don't remember exactly saying this, is because I'm not sure, I don't remember if I exactly said this, but the kinds of things we thought about are the kinds of ways you'd prove this thing. Now, why I gave that sentence is because, and this is also useful perhaps on some of the homework, it's that if you have anything about, hey, I have a graph that's connected, well, every connected graph contains some kind of a minimum, a backbone, some kind of a tree that's inside it. I'm not saying that's the whole graph, but if you have a connected graph, it always happens to contain a tree that goes through every vertex. And that's the important definition we're going to use today. A spanning tree in a graph, what that is that's a collection of, well, all of the vertices are in it, and it's like a collection of some of the edges, possibly all. It's all the vertices and a subset, possibly all. Subset always includes possibly all of the edges such that they make a tree. Now, not every graph has a spanning tree inside it. Because, for example, if the graph you started with was not connected, well, there's no way you could make a spanning tree inside it because that connects everything. But a nice fact, I'll just call it fact, it doesn't deserve to be called a theorem. The fact is that every connected graph contains a spanning tree. Okay. Now, I called it a fact because if you wanted to prove it, it's relatively easy. Because you're like, well, I need to show that every connected graph contains a graph that's connected and has no cycles. How might I do that? Just so that I'm not the only guy talking here. How might you try to prove this fact? It's not crazy. Braden.
While the graph still has cycles, you could just cut out one of the edges of the cycle and still have a connected graph?
Yeah.
You can just keep doing that.
Break a cycle by deleting one edge. So it's just like, it's a while loop. I just go and say, okay, do I have a cycle? I have a cycle. Okay, break it. Do I have another cycle? Okay, break it. And the important thing is that this keeps connected all the time. Okay, and that's because if I had a cycle, then, breaking one thing here, I can go around the other way if I had to. Okay. So now I know that every connected graph contains a spanning tree. This fridge is making a noise. Let me just close the door. Okay, there was just some funny noise from there. Okay, so I know that every graph has every connected graph has a spanning tree, and I'm putting that down because if you ever are thinking about something which is about a connected graph, well, it's always useful to go and say, let me grab a spanning tree inside and see if I can argue about anything in there. And sometimes that's all you need because that serves as a backbone of the whole graph. Notice I use the important word here, a spanning tree. A is not the same as the, because there could be lots of different spanning trees. It's just like if you have a bunch of cycles inside it, you can decide which way you want to, use parts of the cycles. But now today, what we want to talk about is the notion of the best spanning tree, or the minimum spanning tree. Now, usually in life, people are greedy and they want lots of things. They want maximum. But in the context of graphs, oftentimes you're like, I don't know. I want to, I guess, only pay for the minimum number of roads to connect everything. Maybe, maybe you're like, I'm going to make roads. I have these different cities I want to connect. I just want to put in the minimum number of roads that will connect the cities. And that would save a lot of money, right? So minimum is better than maximum. Except that you get the kinds of traffic jams that made me late for the class. So in some sense, maybe like having more than a spanning tree is sometimes useful. But I'm still going to focus on the concept here of minimum spanning tree. A minimum spanning tree makes sense in the notion of a weighted connected graph. I'll call it a weighted. We haven't used that word before, so I'm going to describe it. A weighted connected graph is what it sounds like. Okay, I'm not even going to. Well, it's like least total weight is the one with least total weight. Least total weight. Now, what's a weight? Well, I need to go and describe what that would be. I now will be talking about graphs which are connected, and it doesn't have to be like the complete graph. It's just like I'm going to draw it on the next screen. I'll have a bunch of vertices. And, it doesn't really matter what it looks like, but it's just something. Drew something. Bunch of vertices, a bunch of edges, and now every edge has a weight also. So let's put some random weights on there. The weights, by the way, don't have to be like integers or anything, but they're usually non-negative. They're actually usually positive. 1, 2, I'm lazy. They're all going to be like numbers. 4, 9, 9, 9, 2, 1, and 3. I made up some numbers, okay? So I just made some random numbers down. So if that's my weights on the graph, what would a minimum spanning tree mean? Well, I need to find something that has to go through all of the vertices. That's what the spanning tree would be. And I need to find some way that minimizes all of the weights. So I minimizes the sum of all the weights. So the weight, the total weight, oops, wrong pen. The total weight of a spanning tree is equal to the sum of the weights of its edges. Okay, so that seems reasonable. And how would I find one of those? Which is one? Can we see one? Anyone see a good way to make a cheap spanning tree? I'm just going to be like, I eyeballed it. I'm not even sure this is right, but this looks kind of inexpensive to me. I think. It just kind of looks good because I don't want the $9.99. $9.99 scares me. And seems like it's right. I see a lot of ones in it. It feels good. It's like I got ones. And by the way, I'm lucky. I did not know how easy or hard this would be to do. I just wrote some totally random graph and put some random edge weights, and I hoped that I wouldn't need the pi. And somehow, it's like Yeah, this looks reasonable. But what kind of a proof is that? So now we've got to think. Okay, minimum spanning tree, I have a definition, so it exists. Ooh, what's this? Minimum as in, ooh, yes, 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 yes. Okay, thank you for asking the question. So what I want to do here is we're not talking about the number of edges, because the number of edges will be exactly vertices minus 1. It has to use all the vertices. And we're not talking about minimum in terms of like the lengths of the paths between vertices. We're talking about the actual sums of these things. Think of this as saying, I have a road network that I've built. And like these are only roads I can build. For whatever reason, I cannot build a road from here to there, maybe because there's like a giant mountain in between or something. But like this thing here, if you try really hard, you can build a really expensive road between these two. So the notion is that here are all the pairs of cities, and here's how much it's going to cost me to build all these roads. Some of them are not like even possible. And the minimum weight spanning tree would be one where I've added up the costs of building all the roads, and it's the minimum total cost. And actually, I realized I also made a mention of or the. In fact, there can be multiple minimum spanning trees, just like there can be multiple minimum spanning trees. Can be multiple minimum spanning trees with the same weight. And that's just because, if you had some kind of a graph, maybe you could have like, the same weight one way and the same weight another way. Okay. Now, actually, it's interesting. All of these things here, for the rest of this section, maybe today and tomorrow, or today and the next time, we always call them MSTs because we're tired of writing it all the time. Of course, the annoying thing about that abbreviation is M stands for, is it minimum or maximum, right? So we just will know it's always minimum. Minimum spanning tree is always what we're playing with in this class. And if you wanted to find a maximum spanning tree, turns out that you can adjust the way of thinking, and you'd be able to come up with a way to use these as algorithms to make the maximum spanning tree. Actually, if you look at the old exams, you can go and play with some question. I think there's some question playing about maximum spanning trees. All right. So now we have this notion. We want to find a minimum spanning tree. Well, let's see. At first, actually, it looks like it could be hard. I mean, if what you're going to do is you're going to try every possible tree, which is sort of what I maybe was brain doing a little bit. It's like, what if I use this? What if I use that? That's a lot of compute. Like if I have to go and check every possible spanning tree, that would take forever. So I'm going to say would take crazy amount of time to just consider every spanning tree while you're hunting for the minimum, okay? Because there's like tons of different spanning trees that you could put here. In fact, we might even talk a little bit about, we will talk about a way of counting how many there are later in this class. And there's like an enormous, gigantic number of them. It's more than exponential in the number of vertices if you have enough edges going on. So that's highly impractical. Now the next thing is like, is there any dream of getting a practical algorithm? Because as we said before, like finding this kind of Hamiltonian cycle or even knowing if one exists, that turns out to be an extremely hard problem to do. And to give a sense of why this thing could be a hard problem to do, if I just change the statement of the problem very little bit to say, what if I wasn't interested in the minimum spanning tree? I mean, what if I wanted to know what's the shortest total cost it takes to start from one vertex and walk through every other vertex exactly once. And I don't even care about coming back home, okay? It's just like, I'm going to go from somewhere, I need to go to somewhere else, and I want to cover every vertex exactly once. Doesn't that sound like the same kind of difficulty? Same kind of problem, right? So I'm just going to say like, compared to the problem which is, let's write a colon, versus the problem which is called minimum total weight of a path visiting every vertex exactly once. I don't really need to write the word exactly once because if I visit every vertex and it's a path is not allowed to visit the same vertex more than once, but I'm still just going to write it anyway just to emphasize. Exactly once. Well, doesn't that sound like the same kind of problem? Like over here, I've got minimum spanning tree. I have to go through every vertex exactly once, and I'm allowed to make a tree. And over here, I have to go through every vertex exactly once, and there has to be a path. I mean, come on, this is easier. There are less of these to worry about. Right? Like if you think about it, if my goal was to find the cheapest total thing, if I only have to consider paths, I've got less things to consider. So this should be easier, right? Well, the only problem is this is an extremely famous problem. Is the spanning path a thing? Well, okay. So you're right. Is there such a thing as a spanning path? Well, there is. It's actually called a Hamiltonian path. Which sort of makes sense because we were talking about a Hamiltonian cycle before as going through everything. It's also sometimes called the traveling salesperson. And that should make you scared right away. If you see there's some traveling salesperson involved, well, first of all, that's like a cute sounding name, so it's probably some really hard problem. And it is. The traveling salesman problem, traveling salesperson problem, is this question of how do you find this thing? And by the way, it's like extremely practical. The Amazon guys have to do it all the time when they go and drive around delivering the packages. It's like extremely important problem. There's only one issue. Nobody knows a good solution of it. Nobody knows a fast solution to this problem with the path. And if you did, you'd get really rich because, for example, Amazon would pay you. Everyone would be able to do things better. This problem is needed everywhere, but nobody knows a good solution for it. And it's related to this thing of P versus NP. So unfortunately, this is hard. In the sense that nobody knows how to do it in an amount of time that grows polynomially with the number of vertices. That's actually what the technical thing is. In a computation time that grows polynomially in the number of vertices. Let me explain briefly what polynomially means. Polynomially means like if I double the number of vertices, does my compute time just multiply by 2 to the some reasonable power, like 2 to the power 3? It's like if I double my number of vertices, do I need 2 cubed times as much time? That's polynomial. Or if I like multiply the vertices by 10, is the amount of time I need like 10 cubed times as much? That's a polynomial to the third power. The problem, I mean, that sounds like a lot, but it actually isn't for computers. The problem is if you have what's called an exponential time algorithm or worse. It's like if you look at the function 10 to the power n and you double n, it gets like crazy. It doesn't just multiply by 2 to some power, it squares. So that's just why this is bad. So all this setup is like, this is a really hard problem. Oh, question here. Computer security people's lives wouldn't be better. Yes, that's right. So I mean, like, for all you know, so they're probably, okay. I guess my thing is like, if it was solvable, surely someone would have figured it out by now, given the amount of potential commercial value there is and the amount of money governments might have been investing in to do it. They haven't succeeded as far as I can tell. And unless they're just like decrypting everything and listening to everything we're doing right now. Maybe they are. But I don't know. I don't think that the secret can be kept that well. Although I will say, by the way, that's why I personally refuse to do research in these areas. I don't want to do research in an area where if it's like, my gosh, I just figured out something. That night, like someone knocks on my door and I disappear. Like that'd just be terrible. You know what I mean? It's just like, I don't need to be, I don't like to touch these things. It's too valuable, too important. Let me go and think about some pure math instead. All right. So anyway, these are hazards of like, you know, if you figured out ways to take over the world, then someone will knock on your door. Okay, so now this is bad, right? We now know this is like a very, very hard problem. And here I am trying to teach you how to do an even harder problem. Looks like we have to consider even more stuff. We can't just consider paths, we got to consider crazy things. But it turns out that there's fast ways to do this. Now, that's because it's not actually a harder problem, right? I'm saying I'm allowed to look over more possibilities. And if I'm allowed to look over more possibilities, it just so turns out it's easier to find some of them that work. And it might seem at first a little counterintuitive. Like over here, I'm only looking over paths. And here I'm looking over paths and more stuff. But if I change the problem entirely to say, can you find the minimum total weight of any subset of edges at all? Well, yes, that's called take nothing. I'm done. problem is solved. I don't have to do anything. But the number of subsets I, in theory, had to consider, if I said all possible subsets, I had to consider way more subsets of edges than even just these paths, right? I'm saying, like, just because you allow more possibilities doesn't mean that the problem gets harder, because I just showed you how to trivialize it by saying, I will allow any subset, find the cheapest total thing. Done, take nothing. Okay, so that's just why there's some hope that this could be easier. All right, so now let's start talking a little bit about how you might even try to get an algorithm for this. And this is remarkable, the fact that there is one. The first thing you'd think of is, can I be greedy? Now, let me talk a little bit about what a greedy algorithm is by trying to do it for the traveling salesman problem, trying to like prove that, break through history and say, we can solve traveling salesman problem with the greedy algorithm. Will that possibly work? So here's the greedy algorithm for attempting, it won't work, attempting to solve traveling salesperson. Well, what you could do is you could say, I have some, what would you do? You'd say, find the cheapest possible edge, right? We can decide where we want to start. Find like the cheapest possible edge to start. Find the lowest weight. I guess I should call it that way. Find the lowest weight edge to start. Okay? I don't know what direction to go. Just choose any direction. Or kind of like go in the direction that there's another low weight. Go along it in the direction where there's another cheap, low weight, lowest or low, just low weight. And greedy then just means attempt to keep walking, always choosing to go along the low weight edge. Try to keep walking, always going on the lowest weight edge you can find. Right? So in theory, what's really going on, I have some kind of a graph, right? And I found this lowest weight edge. Oh, look at that. There's some lowest weight edge here, and the lowest weight edge happens to be 5 or something like that, okay? And then you decide, oh, off of these two sides, what did I see? I saw some stuff coming off of each of them, and when I saw some stuff coming off of each of them, what were those weights? They were bigger than 5, because 5 is the lowest. So maybe this is 9, maybe this is 7, maybe this is 6, and maybe this is 6, and maybe this is 14. And then what you say is, yeah, okay, I'm just going to go along the 5 and then like the 6, and you just keep going, right? You go and say, from the 6th thing, what happens? You might come back to one of the vertices you saw before. You might fly over here. You might go there. Maybe there's some weights here like 999, 999, and 999. Now you already see why this is a bad algorithm. It's because if you're just greedy, you can get stuck, right? Like if all you're saying is, I will just attempt to go and, if it's like an earthworm crawling or something, I'm just going to eat the tastiest food I can find as I keep going, you might find yourself running into rocks. And then that's it. No more food. Right? And that's the problem. That's why greedy algorithm is a terrible idea, usually. Now, you can also sort of see, though, how that's why this Hamiltonian path, this traveling salesperson, that's why this is harder. Because you see, worms have heads. The heads have only one mouth. So you only have one way to keep eating. But if you're suddenly going to do the minimum spanning tree, you're sort of like one of those crazy like worms that regenerates things like, you've seen those videos, maybe you cut off the head and then the rest of the body regenerates off of the head. This is like a worm that can regenerate heads off of anything, which I've never seen in my life, but I guess that's called a hydra. That's right, it's a hydra. I guess they don't exist, but in any case, this is basically like a hydra in the sense that when I'm doing a minimum spanning tree, I could grow in any direction. So in fact, there's an idea of a greedy algorithm that we should try, and it even has a name because it actually works. But that's like unbelievable. There's no reason why this should work. There's an algorithm. I don't want to call it a theorem. I'll call it an algorithm, okay? Algorithm, because we're going to prove that it works. Algorithm And this is called Prim's algorithm, Prim. And what this is it says, just do what we just said there, except that you're allowed to kind of go off in any direction. Okay? So again, the goal here is to you're given a connected weighted graph. Okay? Now how would you start? Well, now we're thinking of this as like this hydra which is growing. So step one, just start from any vertex, okay? Because we eventually have to connect up every vertex. Pick any vertex to start. Okay? And then now the important thing is, while you're not done, meaning like you haven't gotten all of your vertices into this graph, while there still are vertices not yet in your spanning tree, in your tree. We don't know it's a spanning tree yet. In the tree we've built. Well, what might be good? I don't know why I wrote a 1, but I'm just going to write some numbers, okay? Because then I can talk about the points. But the 1 is somehow do a 1, and then the while loop is going to do a bunch of stuff many times. Well, I've got some vertices which I've already gotten. And so we're building a tree, by the way. Just like how the worm was kind of eating and growing, we're having this hydra come out, which is growing in some crazy way. We've gotten some tree. This is what we've gotten so far. We've built some tree. Built so far. And then there's like more stuff. There's like all this stuff that we haven't gotten. So let me just put the built so far into this circle. And then here's the rest. I don't know what it looks like yet, but there's the rest. There's some more stuff. Okay. Now, I do know one thing. I know that my graph was connected to begin with. So there have to be some edges that go between, right? There have to be some edges that go across. Must exist, or else it wouldn't be connected. So there has to be some things that go across. There can be multiple things going to the same one. Okay? They can kind of go off in all these random directions. But these must exist. Since we're started off with connected. Does anyone have a suggestion? If you were greedy, what would you choose? I'm trying to build up this tree. I'm trying to build up this minimum spanning tree. I wanted to eventually eat up all of the vertices. Here, I have gotten so far. I've gotten the yellow thing. And it's, what I've gotten so far is sane. What might you want to do?
Maybe you want to choose again the minimum age on the third.
Yeah.
The one that are like that.
Yeah. It's like, I need to grow this thing, right? It's like my hydra is growing from every head at the same time, and I have a few different possibilities. We're greedy. Pick the one that is the cheapest and hope that it works. Okay, so the step 2 of the algorithm is add to the tree we're building. I'll not call it I'll call it a minimum, because if all 3 of these were the same weight, there's no the cheapest because they're all the same. But it won't matter, just pick any one of them. A minimum weight edge from the crossing. I'll use the same pink color from crossing. Okay? And just do it. So it's just like, just do it and do it and do it and do it. And somehow it's going to work. Promise. Well, that's actually a big promise. I'm hoping I've built up by now to make it so people wouldn't believe this. Because what we just saw with this kind of Hamiltonian path, or the traveling salesperson path, is that how could you hope to be that lucky? Like, what if you just did something and you were greedy and you locked yourself into a bad set of decisions? That's actually what we're going to prove next. What we're going to prove next is, it turns out that this choice of grow and always greedily pick a cheapest one that crosses, turns out it's always going to give you a minimum spanning tree at the end. And that's a minor miracle, that if you could be this dumb and this greedy, and the thing that pops out at the end actually is a minimum spanning tree. So the theorem, that finishes the algorithm, by the way. The theorem is, this always makes a minimum spanning tree. We have to prove that. There is something I want to comment. I made some comment about efficiency. Is this like, how crazy is this algorithm to actually do? Do you have to look at exponentially many possibilities? Well, not really. Because if you think about what's going on, what you do is you're only going to examine, is that true? No. So what you're going to do is, as you grow this, right, every single step, let's think of it as growing it step by step by step, right? I'm going to grow it n steps. There are n vertices. So the number of steps is n. Now for each of those steps, I have some stuff here, and I have some stuff there. And I need to go and find out all of the edges that go across. That's at most, I'm being very rough here, that's at most n times n possible edges to evaluate. Probably a lot less, but I'm just saying I have n steps. Each step is evaluating at most n squared edges and finding the cheapest one. And I find it and I add it. I'm trying to emphasize that it's like n times n times n. That's like n cubed or something. You can actually do much better than this. Maybe you can cut it to like n squared. But I'm emphasizing that it's not exponential. It's not like I have to go through lots and lots of possibilities where the possibilities blow up. If I want to do an analogy, if you were trying to find a Hamiltonian path or a traveling salesperson path, and if it was like n vertices, and you started by saying, I want to consider every ordering of n vertices I could walk through, that's n factorial. So I'm trying to emphasize that n factorial, huge. But this is like n cubed or something, or n squared. It won't be that bad. So that's why this is actually efficient. In fact, this is so efficient, you can even do it by paper and pencil. That's also a way I often decide, like, is something efficient or not? It's like, would I be able to do it? And yeah, the answer is yes, I would. Okay, so now let's go and prove that this works. How would you prove that? So you see, if I want to prove that something like this works, I already sort of was hinting at the key concept here, which is called, you never get trapped. You never go in the wrong direction. Because notice with the greedy algorithm, there's no taking things back. You can't be like, oh, just kidding, that was a bad move, I changed my mind. With the greedy algorithm, you say, I want that edge. Okay, you're locked into it. I want that one, I'm locked into it. If at any point you lock yourself into some stuff which has no chance of finishing into a minimum spanning tree, you're dead. And the proof is over. I mean, then there's no proof. But that gives an intuition for how you could prove this. One way to prove this is to show that when you take your steps, every step always has a way to finish. I'm going to write that here as a theoretical concept here, and then we're going to go to another screen and actually go and prove this. So the big idea of the proof is that we're going to show that at every point, the thing that we've built so far is contained in some minimum spanning tree. What we've built so far is always part. I'm going to be very clear. Always entirely part. It's a subset. Entirely part of some minimum spanning tree in the original. I'm just emphasizing like minimum spanning tree in original, but we really just meant that anyway. We always meant minimum spanning tree in the original graph. I'm just emphasizing because we've got like some stuff we've done so far, so at least if you read this, there's no confusion. This is just saying, I need to show that no matter what, as I'm doing this algorithm, this thing I've got so far, that's a part of some minimum spanning tree in the end. And that's like telling you, you'll never take a step and be permanently in the wrong track. Does it make sense that if I could show this, I'd be done? Because then that just shows every step you make, you're always going to be on the right track. It always is contained in some minimum spanning tree. So like take all the steps, and at the very, very end, you took everything. That's supposed to be contained in some minimum spanning tree. Well, then that is a minimum spanning tree. Does that make sense? It's like that's how you get the end game. It's like as long as I can show every step of the way, I am part of one of the minimum spanning trees, because there could be many different ones, then by the time I actually use every single vertex, I'm still part of a minimum spanning tree, but I am a spanning tree. There's no more I could grow, therefore I am a minimum spanning tree, I'm done. I've proved the whole thing. So that's like the intuition for how we're going to make the proof. Okay, how will we prove something like this? Well, the key idea is like, you could call it induction. I also could just think of it as saying, if you can show it was true at the beginning and it stays true, you're good. That's called induction. So let's start at the beginning. How do we know that at step 1, after doing step 1, what we have picked so far is part of a minimum spanning tree? Well, no one's answering because that's like, duh, you have a vertex. If you just have a vertex, that's part of every minimum spanning tree because it has to contain every vertex. So the one part is obvious. It's like, it's duh. Okay? They always say you're not supposed to write like obvious or trivial in a math proof, so I'll write duh instead. But so this one is duh. It's just like, yeah, it's always in math. But now this is the second one, is the one we have to think a little bit. So we have to say, while there still are vertices not yet in the tree we've built, then by adding one of those, I'm still guaranteeing that I'm in a minimum spanning tree. For this, we'll have to do a little bit more thinking. So I'm going to redraw the picture for 2 on the next screen, and we're going to do some more thinking on it. So for 2, what do I actually have? I have some tree, okay? So there's some tree we've built so far. That was supposed to close. Okay? So this is the tree built so far. And we've got the rest. And we have a few edges. Okay, we have a few edges that go across. Oops. I'm just going to draw a few of them. I mean, there's many more, but there must exist some edges that go across because they're connected. So these are the edges across. Okay. Now, there is one of them that we decided to pick. We decided to pick one of them, which is minimum weight. So we actually decided to pick this one. This is one of them, which is minimum weight. It could have that there are multiple minimum weight, but we picked that one. So this one is a minimum crossing. Okay. Now, how can I show that I'm always going to be part of a minimum spanning tree at the end? Well, here's where I need to use the induction hypothesis. It's like, well, here's the thing I've built so far. I get to know that the thing I've built so far, that is legitimately, definitely part of a minimum spanning tree in the end. There might be many minimum spanning trees in the end, but that is part of a minimum spanning tree in the end. So I'm going to use maybe this green. Oh, maybe use white. So this is guaranteed. I know from the induction hypothesis or the previous steps statement. I prefer to use induction hypothesis. Induction hypothesis. This is inside an MST. Okay, what does it look like? Well, I've got some possibilities. What if the MST that it looks like, so it's inside an MST, meaning like there's all of this stuff, and there's more stuff that's part of it. Like, so suppose I had the MST that is part of, I'm just drawing some stuff, it has to all contain this, and suppose the MST is part of, contains this, and then does some more stuff. Well, that would be great. If the MST that it's part of already includes this edge, I have nothing more to prove. It's like, well, yes, then adding this, I'm still going to be part of an MST. Okay, so that's like the easy case. I'm going to remove the highlights so that I can see my picture again. So let's put it here. If this contains, let's give that edge a name, by the way. Let's call that edge E, E for edge. If that contains E, if this contains E, you're already done. Already done. Meaning that if I added that edge E, I'm going to be part of a minimum spanning tree. Okay. Well, why not? What else might happen? Unfortunately, what else might happen is it doesn't contain E. If it doesn't contain E, that's sort of why I drew another edge connecting. The key is that, remember that it's contained in some minimum spanning tree. That minimum spanning tree has to get its way across somehow. It has to be able to get all the way across somehow. So that minimum spanning tree that it's part of, now I'm going to do the white highlight, but a different way. else it crosses some other way. And I also want to emphasize, when it's crossing, it could actually cross over by a few edges. So I'm going to actually, I do want a few more edges inside here. So maybe, yeah, this one, this super big flyover, okay? But that's not really deeply consequential. I'm just trying to say that, what does it mean that it's part of a minimum spanning tree? It could look like this. It could be that the minimum spanning tree goes across this way, and then like does more stuff, okay? And then it's a minimum spanning tree, so it has to use everything. And importantly, notice that the white thing this time does not use that yellow edge. That's important. Crosses some other way, but doesn't use E. I'm actually not going to say this is definitely a contradiction, because I don't need to say that adding this edge E makes the new thing a part of whatever was the old minimum spanning tree that contains this one. As in, actually not that there's only one either. There's like many options, right? So the important thing here is I'm saying there's an MST. So this white thing here, it's not like the only minimum spanning tree that contains the thing I have here. There's many of them, but I just drew one of them. And if we're not lucky and that one doesn't contain this edge E, we're going to show that there is one that contains the edge E, which is at least as cheap as the white one that I've drawn. So the goal is to show there's another MST that, actually I won't call it MST, I'll just say there's another spanning tree, and that's going to be enough. Another spanning tree that does have all of the previous and then plus the edge E, and with less than or equal to the cost of that white MST. The less than or equal to the total weight of the white MST. So I'm just trying to use the colors to code things. The white MST is the one that I'm guaranteed, the minimum spanning tree, guaranteed to contain the old tree. That's the one in white. And the claim is, well, if that one just doesn't happen to use this edge E, well, then I will go and make another spanning tree, and it's going to be less than or equal to the cost of that white one. But the white one was supposed to be minimum, and if you got anything less than or equal to the minimum, you actually are also a minimum. That will do it. So also a minimum spanning tree. Okay, so how might we do that? Anyone have an idea? Like, we're looking at a picture here. Suppose what I've got is, I'm claiming that the white thing is a minimum spanning tree. It's the cheapest possible spanning tree. It's a cheapest possible spanning tree in the entire graph. It doesn't contain this yellow thing. Is there a way to make an adjustment so it contains all of the stuff it had before? It also contains the yellow thing, and its cost is less than or equal to the white one. Any ideas? Remember how you got the yellow thing, by the way, or the pink or whatever. This is the minimum crossing weight. From this side to that side, it's the cheapest one. Aha, Andrew.
So maybe you could look at the cycle that would be formed by adding E and break the longest, something longer than E of that cycle.
Yeah, thank you. So the important thing is, remember, now we're using some properties of trees. The white thing is a tree. That means it's a minimally, it's a maximally acyclic graph. We've talked about that too. If you have a tree which has n-1 edges and it's connected, you add any one edge, and that one edge is going to give you a cycle, and it's going to be part of that cycle, right? So the important thing is, since we started with this white tree, you added one edge on the white tree, bang, there's now a cycle that contains that one new edge. So I am running out of space on this. I guess I can try to squeeze off to the side. Maybe this will fit. So what I want to say here is, okay, very nice. So now if you add this E to the MST, oh yeah, that's white. So the white MST plus this edge E makes a cycle. With E. And what we just used here is because it's a tree. If you add any edge to a tree, you'll get a cycle using that edge. Okay? Now, if there's a cycle with the E, look at that cycle. It does have the E involved as one of the crossings, but somehow you have to have another one too. Because if you think about it, if you're going to walk on a cycle and you've moved from this piece, the stuff you got before, to the new frontier, and you have a cycle, at some point you got to get back to the stuff that you were at before. You might have multiple. It could like zigzag back and forth a few times. That's okay. But the point is, there's going to be at least one other edge where you go back. And the idea is, rip out that edge and put this one in instead. And since this would have been a cycle, you see, I will still have the property that my final thing is still going to be connected. So there's a few things which are going on here. It's like, okay, well, there's the cycle, so now I can stare at the cycle, and it has like, it's connected, it's n, so it makes the cycle. So I can take away any edge from that cycle, and I'll get a tree back. That's the important thing, because I have n vertices, it's connected, and there's exactly one cycle. Break that cycle. Break the cycle with one of the other edges which is crossing. So the next thing is to remove from the MST any other edge that is crossing between the two parts. And add E. Oh, I don't need to underline because here, I guess, I haven't been underlining the rest of them. So, and add E. E I've actually also been making in that pink color. Add E. Terrific. So if I do that, now I will actually be able to still have a tree because I made the cycle and then I broke the cycle a different way. I still have n minus 1, vertices minus 1, many edges, and it's still connected because I just changed from one piece of the cycle to the other. If I have n minus 1 edges, vertices minus 1 edges, and it's connected, it's a tree. And therefore, I have this new tree, and the new tree is still a spanning tree. Its total weight is less than or equal to the total weight of whatever I had in the white thing, because my substitution went from a possibly more expensive thing to the cheapest. That's important. Remember that that was the cheapest. Since E was minimum, or has weight less than or equal to the other crossing edge, the trees, this spanning tree's weight is less than or equal to the original minimum spanning tree. And you're done. That's actually the entire proof. So I tried to fit the whole thing onto this screen. So we have just found out that, okay, well then there's another minimum spanning tree which contains all of the stuff I started with before, plus that edge. And therefore, by doing that step of going to that edge, I'm still on a track that could work. It's sort of like when I was a college student. At some point I thought I might be a math major, then I thought I might be a physics major, then I thought I might be something else. But the good thing is I eventually graduated. Because what was going on was that every path that I was on, I sort of knew, yes, there's still a path to graduation that I can use. Don't, by the way, get onto a situation where you don't have a path to graduation. That's a bad situation. But you see, like, you don't know what you're going to do yet. But just make sure that each of your options you're going on could finish. That's all that's going on here. We're just saying, like, this hydra, which is eating through the dirt pile or whatever, has some path. Like, it went and ate that way, that's okay. There's a minimum spanning tree that does contain that. And then that means when finally you eat all the dirt, oh, well, it was a minimum spanning tree. It's in one, and that's it. There's a spanning tree. So you're done. And that's it. So this is this remarkable algorithm that's just greedy, but the proof actually all fits here. It's just a simple idea of you never get stuck. Okay, and that finishes our class. So I actually have to go, and just like for fun, I'm giving this talk on the CFA lawn like now. I'm actually gonna get to go to CMU and give a talk. So I don't know if anyone knows if is it raining? No, it's not. So I'm giving the talk, but. Yeah, I'm going to be doing something, but you already know what I do. It's like this no-bid stuff. But the idea is I'm super enthused because I finally get to go back on CMU campus and say something. So anyway, I have that at 4. So I will jump on my bicycle probably in about 5-10 minutes to get over there. There's no traffic on bicycles. So is this, if this is efficient, why isn't a solution to, so the important thing here is that the traveling salesman is not the hydra. The salesman cannot be like, hey, just kidding. I am suddenly going to, send my arm that way while my head goes that way. You can't do that. At least not yet. Now, if you're wondering, wait, why doesn't the traveling salesman just like go on a spur and just kind of like go there and back? Well, now the traveling salesman, if you go there and back, you pay twice for that road. Although we are going to talk about something that is based on all this minimum spanning tree that is related to traveling salesmen, and it's related to what I just said about going there and back. Yeah. I think I was just trying to emphasize that it's very amazing that there would be an algorithm like this because the other ones don't. So I don't want people to be like, oh yeah, it's just an algorithm to memorize, yeah, whatever. It's like, it's cool. Like, why does this exist? And also the proof, like the proof is not even crazy. It's just that you never get stuck. So that's what this is. Cool.
Thank you.
Mm-hmm.